So the integral of x to the fourth natural log of 2x dx is one, yeah, Adrian, it looks like one that you could be using tabular integration for, although, differentiating x to the fourth down to 0 is pretty straightforward, but integrating natural log of 2x over and over and over and over again enough times to differentiate x to the fourth down to 0 is a little bit of a pain. And so that's probably not the best way to go, because that's a lot of painful anti-differentiation. You could do that. And the problem then becomes, if you try to just do integration by parts separately, well, our normal rule is take the more complicated thing that you can integrate, which we can integrate natural log of 2x and make that your dv. But that's exactly what tabular integration would do. So since that integration is pretty difficult to do repeatedly, we're going to try and do this actually the other way. So we're going to let u equal natural log of 2x and let dv equal x to the fourth dx. And so then du will be 1 over 2x times 2, right? Or just 1 over x. And then our v, 1 over x dx, and our v will be x to the fifth over 5. Everybody good with giving it a try that way? All right. So this ends up being x to the fifth natural log 2x over 5. So u times v minus the integral of v du, which just is x to the fourth over 5 dx if you simplify the x to the fifth over the x part. And then that's just a really simple integral. So x to the fifth ln 2x over 5 minus x to the fifth over 25 plus a constant. Does that make sense, Darius?
Yeah, I said a lot. Thank you.
Yep, no problem. Oh, sorry, I missed these things in the chat. Yeah, all right. Ryan, you good with that? 1 over x, yeah. You good there, Ryan? Okay, yeah. All right, so let's move on to some new stuff here. We were working on, let's see, some of these trig ones yesterday, right? I think we finished we did tangent cubed, I think, right? We were on to the next one. Or did we not do tangent cubed? I think we're up to tangent squared secant x. Yeah, okay. So any thoughts on how we're going to go about that one? This one's a little bit longer, a little bit more complicated, but it's going to give us a result within it that we might want to know in the long run. So any ideas? Anybody see a good u substitution there? No, nah, me neither. So let's rearrange some of the tricks. And I can't do secant, because if I let u equal secant, Adrian, then my du would be secant tangent, and I don't have another secant to go with it. So that's not going to work out. So what we're going to do is we're going to rewrite this as an integral of secant squared x minus 1 times secant x dx, or effectively an integral of secant cubed x minus secant x dx. Which, at least part of that, we know how to integrate, right? We know how to integrate the secant x because we did it the other day, right? The integral of secant x is natural log absolute value of secant x plus tangent x. So let's separate this into two integrals. One that's the integral of secant cubed x, and then minus the integral of secant x. Don't forget my dx is on there, which gives us an integral of secant cubed x minus the natural log of the absolute value of secant x plus tangent x plus a constant. Good? Everybody good with that? Yeah, no, maybe. Okay, so then from there, what we're going to do is we've just got this other integral here, just the integral of secant cubed x. And so oh, sorry, no, I forgot my dx right there. So hold on one second. Sorry, my kid was back in here again, sending him back to his class. All right, so no, that's not all under one integral, Nick. Sorry about that. I just forgot to write my dx. So we do need to find the integral of secant cubed x. And so any thoughts on how we're going to find the integral of secant cubed x? Back to tangent. Yeah, so we could potentially do that. And I think what ends up happening if we turn part of that back into a tangent is we're going to end up just having everything cancel out and it coming back to 0, which is something that sometimes happens when you rearrange trig functions and try to do some of this integration. So that's not going to end up working out, Adrian. And Nick, 1 over cosine cubed isn't going to work out either. Okay, we could rewrite it as secant squared. That's right, Darius. And then we're going to try to use integration by parts. So that's what we're going to try and do here. If we wanted to do that, we could say that u was equal to secant x, and then dv was equal to secant squared x dx, which wouldn't be so bad because the integral of secant squared, v would just be tangent x, and then du would be secant x tangent x. So let's see what we end up with. We end up with u times v, so secant x tangent x, minus the integral of v du, which is secant x tangent squared x dx. And then we still have a minus natural log absolute value secant x plus tangent x attached to it. I'm going to leave off the constant for right now because we're going to have more constants here in a bit. Everybody good with that? And what do we do next? What do we notice? Yeah, there's a piece that's the same as the original one, right? So we can say this is equal to the integral of tangent squared x secant x dx. And if we bring this secant x tangent squared x dx over, we end up with, now I guess a new page here. Maybe, there we go. We end up with 2 integrals of secant x tangent squared x dx is equal to secant x tangent x minus natural log absolute value secant x plus tangent x. And then we just divide by our 2. So we end up with the integral of secant x tangent squared x dx equals secant x tangent x minus natural log absolute value secant x plus tangent x all over 2 plus our constant. Everybody good with that? Any questions, issues, problems there? So you could probably see that for a lot of these integrals, you kind of need to get creative with how you solve them. Sometimes you need to rearrange the trig. Sometimes you need to do integration by parts. Sometimes you're going to have the integration by parts that works out nicely. Sometimes it's not going to work out so nicely, and you're going to have to like come back to your original and combine them together. One thing that does happen sometimes with integration by parts is you come back to the original, but you have like a negative of it. And then so when you, or like you have a positive one of it on one side and a positive one of it on the other side, and you subtract and you end up with none of them, in which case you've done something, you haven't done something wrong, but you've just taken a path that doesn't work and you need to find a different path. So it requires a little bit of creativity. Any issues, any questions with any of this so far that we've done with any of the integration by parts or any of the trig stuff? All right, let's keep moving on then. We got a few more minutes here. Sometimes we might end up with something like the sine of mx cosine of nx or sine mx sine nx, you know, or so on. And so for these ones, there's an easy way usually to do them, which is using the product to sum identities. You can also do integration by parts on some of these, and they work out just fine. I think I had one on here on the homework last night that you could use integration by parts to solve. But it's often a lot easier if you use the product to sum identities, which you don't need to have memorized, but just know that they exist, know where to find them, and know that you can apply them in this situation, especially when you move on to some higher up math classes or trying to apply this in some sort of physics situation. You might, you know, in higher physics classes, might help you out and save you some time. So hopefully you guys remember your product to sum identities, at least vaguely. Oh, sorry, Nick, I just saw your question there. So the best strategy to determine which function you want as u and dv is you want dv to be the function that is the most complicated, but can be fairly easily integrated, generally. So that's not 100% the case, but generally, if you can fairly easily integrate dv, and it's, you know, and it's the more complicated one, choose that. Otherwise, try it one way, see what happens. And sometimes you can, you know, there'll be multiple different ways that'll work out with integration by parts, and you could do it one way or the other way, and it'll work out just fine. But generally, the more complicated but still fairly easily integrable piece should be dv. Does that help? So like that one that Darius asked about a little bit ago, it was what, x to the 4th natural log of 2x. Well, we could see that, you know, the natural log of 2x is clearly the more complicated piece, but it itself is fairly easily integrable. But knowing that you're going to have to do it multiple times, you're going to have some really painful integrals to deal with. And so maybe better to try it the other way. All right, so for this first one, sine 2x cosine 3x. I believe there is a product sum for sine of mx cosine of nx. Hopefully you've got your trig sheet in front of you to check that what I'm doing is correct. But I believe it should be an integral still of, and I'll put the 1/2, it's always 1/2 in front of these. So 1/2 of the integral of the sine of the two angles added together, and then plus the sine of the two angles subtracted. Does that look familiar to people? those of you looking at your sheet right there in front of you? All right, cool. I think that, yeah. Haven't used those in a while, so I'm hoping I still remember them. So then we might want to remember also, just to make life easier, with the sign of negative x, that the sign of negative x is equal to the negative sign of x. So I could just make that minus sine x dx, just using the even and odd identities for trig functions. And then we'll just integrate that. The integral of sine of 5x is what? Should be negative 1/5 cosine 5x. And then the integral of negative sine is just positive cosine plus your constant. Good or no? Okay. What about sine 3x, sine 4x? So sine of mx, sine of nx has also got a nice product to sum one on it. Still has a 1/2 out in front, so it should be 1/2 the integral. And I believe this one's both cosines, and it's subtraction and then addition. So cosine of negative x plus cosine of 7x. Somebody maybe check that on your trig sheet just to make sure I got the right one there. Is that one the right one, Adrian? I know you checked the last one, so. All right, we're going to assume it is. All right. And what's the rule for cosine of negative x using the even odd identities? That should be just cosine of x plus cosine of 7x dx. And then when you integrate that, you get 1/2 of integral of cosine is just sine. And then the integral of cosine 7x is 1/7 sine 7x plus your constant. Everybody good with that? Yeah, it is minus in the middle. Sorry, my fault. Let's change all those. Oh, I put a minus in the, weird. Accidentally put the right thing in the last one. Yeah, those are all minuses. That's right. It's been a while since I've used those all. All right, and then the last one, cosine 5x, cosine 2x. Same basic concept. I think this one, I'll try and get this one right. 1/2 the integral of this one, I believe, is also both cosine. So cosine, and now it's 7x, and now it's a plus between them, I think, and then subtract the last two. Does that look right for that one? Yeah, okay. And so then we'll integrate those. No even odd identity stuff to use there. So this just becomes 1/2 of 1/7 sine x, or sorry, sine 7x plus 1/3 cosine 3x plus your constant. And I said, I don't know why I wrote a cosine instead of cosine. I just looked at the function sine there. All right, everybody good there? Any questions or issues? Those pop up here and there, so just good to know those. Everyone okay with that? Okay, I'm waiting. Am I waiting for a reason, Molly? Okay. The middle one, why is the 1/2 negative? It's not. It's 1/2. Oh, that's just an equal sign. Just not a very good equal sign. Still not a very good equal sign. Now it's a better equal sign. Good now? All right. Okay. So it looks like we're going to be done with trig stuff. That's pretty much everything with the trig stuff, but no, actually it's not really. We have these things that we call inverse trig substitutions to help us integrate some other functions. So we're going to at least briefly touch on this, and then we're going to practice this a bunch more next week. Anytime you have an integral, well, not anytime, but most times when you have an integral that has root a squared minus x squared in it, you're going to want to make a substitution where x is equal to a sine theta, and it's going to make the integral a lot easier. Most of the time, if you have root a squared plus x squared, you're going to make a substitution where x is equal to a tangent theta, and it's going to make life a lot easier. And most of the time, if you have root x squared minus a squared within an integral, you want to make a substitution where x is equal to a secant theta, and it's going to make life a lot easier. We'll see sort of why those work out in a bit, but we'll talk about that in a minute. That doesn't mean that every time you see one of these that you have to make this substitution. There might be an easier way, but usually this will be the easiest way. And sometimes if these aren't inside of a square root, if they're inside of like a, to the 3/2 power, you still might want to do this. And even occasionally, if like, let's say you just have a squared plus x squared, you might still want to make the substitution where a is equal to tangent theta, and you might be able to work through it. So this is something you'll want to memorize and know that 99% of the time, if you see one of these three terms, you want to make one of these three substitutions. The theta comes from a right triangle, Nick. So, all right, well, we'll just talk about this real quickly now, because why not? So here's theta on a right triangle, right? Yeah. And so what is this telling me? X equals a sine theta is telling me sine of theta is equal to x over a. So that'd be opposite over hypotenuse. And so what would this other side be? That other side would be root a squared minus x squared, if we're talking about a sine theta. And so I'm talking about a tangent theta. There's my theta, there's my right angle. If tangent theta is x over a, that'd be x, that'd be a. Pythagorean theorem tells me that'll be a squared plus x squared. And likewise with the last one, there's theta, there's your right triangle. Secant theta is x over a, that's hypotenuse over adjacent. And so then this last one here will be square root of x squared minus a squared. And so we're basically just using these different right triangles, using different trig functions on each one to turn it into something that's in terms of theta that I'll be able to integrate more easily. And then I'll convert back to x in the end. So that's where those are coming from. Oh, let's see, where does the theta come from? But do you plug it in? What do you mean, do I plug it in? Not sure what you mean by that. Okay, all right. Let's do an example, since you think it'll make more sense after an example. So what do I have here? I have an integral of root 9 minus x squared over x squared. And so what do we see there? We see a root 3 squared minus x squared, right? That's a root a squared minus x squared. And so based on what we just said, we want to make a substitution, and we'll make the substitution that x is equal to 3 sine theta, right? A sine theta, 3 sine theta. Everybody good with that? Any issues there? Okay. So if x is 3 sine theta, we're going to need to figure out what dx is. So what's dx? Dx would be 3 cosine theta d theta. And so when I plug in my x's as 3 sine thetas, and I plug in my dx as 3 cosine theta d theta, I'm just going to have an integral that's all now sitting there in terms of theta, and I should be able to integrate it. So this integral becomes the integral of the square root of 9 minus 9 sine squared theta over 9 sine squared theta times my dx d theta, which was 3 cosine theta d theta. And so we look at that and we say, wow, geez, we've sure made that a heck of a lot more complicated. But in reality, we haven't, because a lot of this trig is going to simplify down really nicely. So if we have something, what can we factor out of this 9 minus 9 sine squared theta? Should be able to factor out a 9 from that, right? Everybody agree we could factor out a 9 from the 9 minus 9 sine squared theta? I hope. And then we can take that 9 and pull it outside of the square root as a 3. So I'm going to have a 3 times a 3. Well, I'll just write it all out. We'll have 3 times the square root of 1 minus sine squared theta times 3 cosine theta over 9 sine squared theta d theta. And so the 3 times the 3 divided by the 9 should all cancel out. What's 1 minus sine squared theta? Should be cosine squared theta. Then we have another cosine theta and a d theta. And we have just a sine squared theta in the denominator. And the square root of cosine squared theta is what? Just cosine theta, right? So cosine theta times cosine theta is cosine squared theta over sine squared theta. Ought to be an integral of cotangent squared theta d theta. And how do we integrate cotangent squared theta d theta? We need to use a trig identity and turn that into an integral of cosecant squared theta minus 1 d theta, which gives us what's the integral of cosecant squared. It ought to be negative cotangent theta. And then the integral of minus 1 d theta is minus theta plus a constant. And that's not our final answer, but everybody good up to that point? Okay, so if we have negative cotangent theta minus theta plus our constant, let's go back in, draw this triangle, right? There's theta. We had that x was equal to 3 sine theta, right? X is 3 sine theta. That means sine theta is x over 3, making this adjacent side that same thing that we started with, root 9 minus x squared. And now we can just use this right triangle to evaluate what's the cotangent of theta. So what's the cotangent of theta? It should be, and it's negative, right? It should be negative adjacent side, root 9 minus x squared over opposite side, which is x. And then minus theta, well, if x is 3 sine theta, x over 3 is sine theta. And what's theta equal to? The inverse sine of x over 3. And then plus our constant. Everybody good with that or no? Any issues there? Any problems with that?